All right, here we are, and we're going to go ahead and do homework 4. We want to measure the density of the fluid. And by the way, if it'll make you feel all big and bad and cool, I got this problem from an MIT thing, okay? And again, as I always say, this is the same. We teach you the same things at UNO that you learn at MIT or Berkeley or Stanford or Michigan or University of Texas or wherever, and you can get as good an education as you want as long as you don't cheat. Okay, so I know this because I taught this course at Berkeley. So, well, I co-taught. I was the TA, or what they call the GSI. But anyway, so we want to measure the density, row 2, of this fluid over here. Okay, so this is what we're looking for right here. Depicted in the figure by attaching a manometer containing a fluid of known density, row 1. Okay, so this is the known. Both the manometer and the tank are open to the atmosphere. And then we've got all this geometry. Okay, so what we're going to do here is we're going to derive an equation, blah, 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 row 2. Okay, so I'm going to do a given required in solution, and I'm going to do it all over here to the right here. Okay, so again, I'm going to use a straight edge here because I want to prove that it doesn't take that long, okay? Because a lot of you just aren't doing it, and it's like, I don't want to draw a picture. Okay, well, we're going to start at 130, maybe 145, but we're going to use a straight edge, and you're like, I don't have a straight edge. Well, I'm going to use my UNO ID. Okay, you can use your driver's license or a UNO ID or anything like that. I'm sorry, there's a trash truck outside. Anyway, so what we're going to do is we're going to do the givens, and we're going to do this all properly. Okay, so we're going to start at 150. And we'll time how long it takes to do this with a straight edge. Okay, so we've got this manometer, and it's not necessary to, smack your lips while doing this, but sometimes I do. Okay, and let's see. So we're kind of keeping track of what's going on over here. And, it doesn't have to be perfect, but we want it to be good, right? You want to turn into something that you're proud of. And this should be the case for all of your engineering classes. Maybe not perfect, and some of you guys are much more perfect than I am, and I'm always really happy to see it. And if you're doing this right with a pencil, then you can erase things and make it pretty darn perfect. Okay, if you're doing it on a tablet, you can also, you can erase perfectly, which is like super cool, right? And I'm sure that I might have to do that, right? So you can see what we're drawing here. It's not going to take very long. And maybe we'll clean it up with an eraser if we need to. Unfortunately, my tablet eraser is a little bit finicky. It does not always want to do what I want it to do. So anyway, so there you go. And so what we have, and again, I don't usually like to draw the surface of the fluid with a straight edge, just because the surface moves around and stuff, right? So, but anyway, so here we go. Okay, and we've got 2 free surfaces here, and we've got a height. We've got this edge right here, somewhere down here. So the coolest thing you can do here, the best thing you can do, is if you have colors, is to use them, right? You don't need a straight edge for these, right? But that is that's row 1, okay, because that's fluid 1. Okay, and then this is going to be row 2 over here. Okay, and it's like, well, you got the colors, might as well use them, right? On my key, you won't see colors because I did it all in pencil, right? But I did use the tick marks in different directions. Okay, now we've got some distances and things, right? So I kind of like dotted lines here, like that, and I like a dotted line here. Okay, and then again, what is that distance? Well, let's see, what do they call it? They call that H. Okay, and they call this one going down to here HM, which makes me think that this unknown liquid might be supposed to be mercury, right? 'Cause I don't know why they call it H. Oh, head of the manometer. Sorry. It's almost even obvious. Okay. And then there's an H sub T, which I find to be an interesting one, which is the distance down to this opening, right? And we will wonder, among other things, does that distance matter? Okay. And the answer is it doesn't matter, right? And what's interesting is, and we're going to discover that as we go through this, but it doesn't matter where this opening is, okay? It doesn't matter if the opening were there, or if it were there, or if it were there, or if it were there. Okay, what matters is the distance from the surface of the water, or of the green liquid, to the bottom of the green liquid. Okay, that distance matters. Okay, anyway, so that's what's given. Okay, notice, would that take me 3 minutes? Okay, not too long. Okay, required. We want to know, okay, using what we have here, and I'll go ahead and solve it over here so that we can kind of keep everything on one page. But what we want to know is we want to know rho 2. Okay, we're looking for an expression for rho 2. And I want rho 2 as a function of rho 1 and any heights that we might have. So h, hm, and ht. Okay, so that's ht is height of the tank, hm is height of the manometer, and h is just some difference in heights. Okay, and anything else given, but I think those are all the givens. So we're just going to go ahead and do like that. Okay, and that equals what? All right, so we're going to solve this, and the way we're going to solve it is I'm going to just work through my fluids, okay? And the nice thing about hydrostatic law, and this works with all manometers, is we're just going to walk around. Now I'm going to use red to keep track, and we're going to start here. I'm going to call this point 1. I'm going to call this point 2, just because. Okay, so I'm going to start at point 1, okay, the pressure at 1, and then I'm going to go down until I'm right here. Okay, so that means I went down in the fluids. I'm going to add, and that's going to be the gamma of 1 times whatever that height is. Okay, so that's h sub m. Okay, now I'm going to move from there to here, and that's moving horizontal, so that doesn't matter. Okay, now I'm going to move back upwards in the fluid, so I'm going to go from here, and I'm going to go up here, and then the horizontal doesn't matter, and then I'm going to go up here. So I'm going to do it as if it was all one movement from here to there. Okay, because the sideways doesn't matter. So I'm going to go minus gamma 2, okay, times whatever that distance is. And that distance is hm plus h. hm plus lowercase h. Okay, and that gets me to the pressure at point 2 equals P2. Okay, so now we're ready. Now we're cooking with gas. Okay, the only last thing that we want to do before we solve this thing all the way, which I'm going to do in black because working in red bothers me, is note that P1 and P2 are both on the surface, so these are both atmospheric. So this one is PATM. Okay, this one is PATM. And I'm looking to solve for rho 2. So rho 2 is buried in here. Okay? So again, here, what's interesting here is it doesn't matter if I do gauge or absolute because the atmospheric pressure is the same either way. So I subtract that from both sides, it just goes away. Okay? And I'm left with rho 1, which can be written, gamma 1, which can be written as rho 1 G H sub m. Okay, minus gamma 2, which is going to be rho 2 G H sub m plus H equals 0. Okay, those G's are going to cancel. Okay, and I'm left with, let's see here, I'm trying to solve for rho 2. So I'll bring it over to the other side, and I'll say rho 2 hm plus h equals rho 1 times h sub m. And then we're going to solve this, and I'm going to say, well, rho 2 equals gamma 1 h sub m over h sub m plus h. Okay? And we notice that the units are going to work out here because this is length over length, so it has no units. And then this has units of density, this has units of density. Okay, so we're good. And I wish I had boxed it before I started drawing arrows all over the place. But that's it. Okay? Now, the other thing that I want to note before we completely go away from this is if you look at this question right here, or this right here, or really if we wanted to put the G's back in, okay, then what we've got is this is a pressure, and this is a pressure, okay? And rho 2 GHM plus H, where does that? Let's see here, rho 2, so that's this density over here, okay, times H plus HM. So that is the pressure, if I go straight down, that's the pressure right here, okay, from this side. So that's basically the pressure pushing right here. Okay, now the other side of the equation, rho 1 GHM, okay, here's rho 1 is all of this stuff, okay, GHM. So this is this distance right here. So that is the pressure right here. It's the pressure pushing down right here. And incidentally, it's also the pressure pushing up right here. Okay, so because it's at the same depth. So basically, what that equation says, it says what's pushing down right here has to equal what's pushing up right here. Or else it's going to move. It's going to accelerate. Okay, and so this is why it's called hydrostatics. Okay, so this is your solution. Okay, come see me if you need any help. Okay, and again, fluids is important. Fluids is cool, but you're cooler and you're more important. So take care of yourselves. All right, goodbye.